Hi everyone, this video is going over some vocabulary that you need for the new polynomial unit. So you should remember by now that the degree is the highest exponent. So just be sure you analyze your polynomial rule very carefully. The highest exponent is not always going to be first. Sometimes they try to trick you. Typically, we try to write a polynomial in order from the highest exponent to the lowest exponent, but if the question says find the degree of the polynomial, I don't want you to get used to only looking at the first term. So for this, my highest exponent is 3, so that would actually be the degree of my polynomial. You can tell a lot about the shape of a polynomial by the degree and by the leading coefficient. So again, the leading coefficient is not necessarily going to be the very first number that you see. The leading coefficient is in front of your x with the highest exponent. So for mine, -9 is my leading coefficient. And I'm running out of room, but leading coefficient. So that's what these positives and negatives are for. If you have a positive leading coefficient or a negative leading coefficient, it's going to affect the shape of your graph because that's like a reflection over the x-axis where we have that negative out front. All right, so a lot of this has to do with end behavior. So if that was something that you struggled with in the first unit, it's going to come back so you have more opportunity to ask questions and figure out how to correctly write end behavior. But if your degree is even, your left and right arrow should both be facing the same direction. And I purposely left the middle of this graph blank because these polynomials might start to look really crazy. So it doesn't matter if it's just connected. There could be a few like little maximums and minimums, like hills and valleys along the way. But even degree polynomials have arrows that face the same direction. So if your leading coefficient is positive, they should be facing up. If your leading coefficient is negative, they'll be facing down. Odd degree polynomials have arrows that are going in opposite directions. So the range of all odd polynomials is -infinity to +infinity, because anything with an odd number as a degree should have an arrow going down and an arrow going up. Whereas for the even degree polynomials, your range would include whatever the maximum or minimum was for that graph. All right, so positive leading coefficient, I am going to kind of connect this just so you can see, but it should kind of look like it's going up. It doesn't matter how many hills and valleys. If you connect the left arrow to the right arrow, it should look increasing. Negative is if you connect the left arrow to the right arrow, it doesn't matter what else was going on, it looks kind of decreasing. That would tell you that your leading coefficient was negative. All right, and you should pause the video and copy this down. Go back and rewatch it if you need to. This is all really important vocabulary. All right, so you need to get in the habit of going back and forth between these words that mean the same thing. If I ask for a root, if I ask for an x-intercept, I could ask for the 0 or a solution of the graph. They all mean the same thing. We use these to find factors, but a factor is not identical to what these are asking you for. All right, this is a new word. It's going to come up a lot. Figuring out the multiplicity of a root or an x-intercept. So these graphs should look familiar, and it has to do with what does the graph look like where it's crossing the x-axis. So if this was my x-intercept, see how it's going straight through my x-intercept? So this has a multiplicity of 1. And when the multiplicity is 1, we usually don't worry about saying that it has a multiplicity of 1. We just kind of list the root. So this root, however, is not going through the x-axis. It's hitting the x-axis and then bouncing off. It's creating that parabola shape directly on the x-axis. So that has a multiplicity of 2. And we usually call it a double root, or it says a multiplicity of 2, whichever way you want to say it. All right, and then if we look at this closely, the way that this is going through the x-axis. It's not straight, but it looks cubic as it's going through the x-axis. So if it looked like that, it would have a multiplicity of 3. All right, now the reason that that is important, there is a theorem called the fundamental theorem of algebra, which you do not need to know that word, but what you need to know is the total number of roots has to equal the degree of the polynomial. So if you have a polynomial that is a 5th degree polynomial, you have to find a total of 5 roots. And so that might mean that you have to count the same root multiple times. There is also imaginary roots, which we do not have to find, but you need to be able to tell me if you are missing roots, then those roots that you're missing are imaginary. So the total number of roots means real plus imaginary. Real roots are your x-intercepts. And so if it's not adding up, then that means you have imaginary solutions. So I'm just going to draw a graph. And it's a little bit different. If I give you an equation, you should be able to tell from the highest exponent how many roots you're supposed to be looking for. But I'm just going to give you a graph. All right, so I can tell just from the shape of this graph that my degree is going to be an even number and my leading coefficient will be negative. And if you don't understand why that is, go back to the chart that I drew on the last page. So just pause the video, go back. But I can tell that this has a even degree and a negative leading coefficient. All right, so I'm going to start by finding all of the real roots. So I'm going to look at my x-intercepts. So I have an x-intercept here at -3. I have an x-intercept at -1. And I have another x-intercept at +3. Because -3, it's going through straight, that's only going to count once. But look at the shape that it's making where it's crossing at -1. It's not even crossing the x-axis. If I were to cover up everything else and I gave you that graph, you would probably tell me that was a parabola. So a parabola has a degree of 2, which means this counts twice. And so you can tell me that it's a double root. You can tell me that that has a multiplicity of 2. I'm going to actually list it twice so that when we're counting, you can see why I listed it twice. All right, and then 3 is a single root because it's just going straight through. So this has a total of 4 real roots. Even though there's only 3 different numbers, and remember what I said, I can tell by looking at this graph that my degree is even. So even though there's only 3 actual different numbers, -1 has a multiplicity of 2, which means we literally count it twice. So I have a total of 4 real roots. Now, I can't find imaginary roots from the graph, but I can tell when there are imaginary roots from the graph. So anytime it looks like a curve in the graph is supposed to go to the x-axis, but it doesn't quite make it there, then that's where you're going to have an imaginary root. So I'm just going to trace the graph. So see how this turn is going up forever, All right, so now it's coming back down. Well, it came back down and it hit the x-axis, so that's good. That was my real root. But then I'm going up. But see where I'm coming down, but I'm not hitting the x-axis, but it still kind of looks like a parabola. So it should have that kind of parabola shape most of the time. That's not 100%, but all the ones where I don't give you the equation, if the only thing I'm going to give you is the graph, this is what you're looking for. That parabola shape where it's going down, but it doesn't make it to the x-axis, and then it goes back up. So this, the fact that it doesn't reach the x-axis, it went down, but it did not reach the x-axis. This turning point means you have some imaginary roots, and it will make that parabola shape. Imaginary roots always come in pairs. You can never have a single imaginary root. I don't know if you remember back from Math 2, but imaginary numbers come from taking the square root of a negative number, and that process of going through the quadratic formula, which the quadratic formula always gives you two roots because you do the positive and the negative. So if I were to actually work this out, if I gave you the equation, which I didn't, it would be like taking the square root of a negative number in the quadratic formula, and that will always yield two answers because it's always going to give you the positive version and the negative. So I would technically write that if I wanted to take the square root of -4 as positive and negative 2, and then a cute little fancy I for imaginary. We're probably not going to have to do that, but I just wanted to show you in case it comes up on something else as we're doing it.